Okay, so moving on to week 12, we have interrupts first. So interrupts are, it's a way for us to get input or get updates from maybe our peripherals or maybe inputs, and then address them as they come. So parang in contrast to polling, where in polling we wait for a certain event or a certain input to occur. So parang nawawala, hindi na natin siya kailangan hintayin. Pwedeng sabihan na lang tayo pag andyan na siya, basically, when we use interrupts. So for interrupts, yun nga, multiple interrupts can occur at the same time. And ayun, ang priority ang sinusundan natin para malaman kung aling interrupt yung unang papansinin. And then interrupts can also interrupt other interrupts, and that is called interrupt nesting. And then yung priority rin yun na determine if kayang i-overwrite or i-mask ng isang interrupt yung another service na interrupt. And then yung ating interrupt is ginagawa niya is nati-trigger siya ng pag-run ng specific set of commands called the interrupt service routine or ISR. And yung ISR na to is stored also in memory, just like any other set of commands or instructions natin sa microcontroller. And ayun nga, since medyo special siya, medyo hindi siya yung, wala siya sa normal na location na memory. It's in the, it is specified by the interrupt vector kung nasan siya in memory. So medyo out of the scope naman ng ating discussion kung saan siya exactly, but it's enough for us to know na meron tinatawag na interrupt vector. So after our interrupts, one of the most common interrupt sources are our timers. So timers are basically counters na ating clock cycles or input transitions. So in configuring yung timers, we mostly want to determine first ano yung actual time duration na kailangan, and then identify the total number of cycles using the given clock para makuha yung time duration na yun. And then we get the prescaler and the period register values depending on the dun sa needed na delay. So let's look at yung formative quiz 1 for week 12 sa ating UVLE page. So actually I have it preloaded over here. So basically 5 questions, and the first one is determine which of the following statements are false. Actually, isa lang. Which of the following is false when talking about interrupt nesting? So recall, nesting is yung pag nag-interrupt ang interrupt with another interrupt. So first statement is an ISR can be interrupted by an interrupt with the same priority if it has a higher sub-priority. So this is actually false. So a difference ng sub-priority and priority is that sub-priority is just relevant pagka sabay ang dalawang interrupts. But if an interrupt is already running, kahit na maximum sub-priority siya, hindi niya kayang interrupt ang isang ISR na same or higher priority. So actually, yun ay sagot. But let's just go over the other statements. So an ISR can be interrupted by an interrupt with a higher priority, of course. And then interrupted ISRs will still continue after the nested interrupts has been serviced. So kaya nga siya interrupt nesting. So for example, meron tayong main code over here. And somewhere in the middle, in-interrupt natin siya. So pupunta tayo sa ISR. And then somewhere in the middle ng ISR, na-interrupt siya. So para lang siyang stacking ng functions. So ito yung last ISR. And then pag fully finished na siya, babalik siya dito sa naunang interrupt. And then after nito is babalik na siya sa main code. So kaya siya nesting kumbaga kasi parang Nagsa-stack siya inside one of the other. So parang yung mga doll, na nesting doll. So meron tayong maliit na doll sa gitna. Tapos tatakpan mo siya ng another larger doll. Tapos yung largest doll. So parang nesting. Lastly, if multiple same priority interrupts occur at the same time, some priority will determine which is serviced first. So actually, ito yung main reason kung bakit meron tayong interrupt side priority. So this is also true. So true, true, true. Only thing false is letter A. Okay. Next question. You are to configure a 12-bit timer to generate a delay of at least 10 milliseconds with an input clock of at 10 megahertz. Find the minimum prescaler and period register values needed, assuming one additional cycle is needed for rollover. So one thing to note here is minimum prescaler needed. Kasi pwede naman natin piliin yung highest prescaler and yun na yung pwede siyang maging tamang sagot. So para naman lagyan natin konting challenge, hanapin yung minimum na prescaler na kailangan for us to generate the 10 megahertz delay. So makikita rin natin dito bakit merong minimum prescaler. So first, let's get yung number of cycles na kailangan natin. So we need to generate 10 milliseconds of delay. And we have a clock at 10 megahertz. So that means 10 times 10 to the 6 cycles per second. So if we want 10 milliseconds and we have 10 million cycles per second, that leaves us with calculator. Times 10 to the 6. So 10 to the negative 3 times 10 to the 6. That is 100,000. So, well, if we need 100,000 to count 100,000 cycles and we only have a 12-bit timer, so a 12-bit timer, that means yung maximum value niya is 2 to the 12 or 4096. So, we actually need to use a prescaler kasi we can't store 100,000 sa ating 12-bit na timer. So one way to get yung ating prescaler is just divide lang natin ito by 4096. So we get 4096. We get around 24. So looking at yung available na prescaler values sa atin, we only have 1, 8, 64, and 256. So can we choose 1? Of course not. We can't choose 8 as well since it's lower. So ang option na natin is 64. So that will be our minimum prescaler needed. So you may ask, bakit 1, 8, 64, 256 lang yung meron dito? We can check yung datasheet. And sa timer control register natin, you can see here, yung prescaler select bits natin for the PIC32MX family is yung 1864256. So yun yung mga usual values na available. So, and since we are using a prescaler of 64, we can divide yung 100,000 by scalar. Since the prescaler, kumbaga every clock cycle or every 64 clock cycles, tsaka lang mag-tick yung ating timer. So we can divide yung total number na required by 64 to get 100,000 to 64 to get 1,562.5. So we need to get at least 10. So, kailangan natin mag-overshoot ng konti. So, we can either use 1562, go below, or 1563. So, ito will be slightly longer. This one will be slightly shorter. But since we need at least 10 milliseconds, ito yung for sure na 10 milliseconds. And then, so 1563, and then reducing the one additional cycle needed for rollover, what we write as our answer is 1562. So if this was at most 10 milliseconds, kunin natin yung 1562 and 1561 yung sagot natin dito for the period register. So, and similar question down here below, but instead of a 10 megahertz clock, we have a 2 megahertz clock. So we can modify our equation. So palitan natin 8 dito. Release natin ito. So instead of dividing it by 8, multiply it by 10 million cycles, we multiply it by 2 million cycles. So that gives us 20,000. And if we divide this by 4096, we get 4.88. So looking at yung available na prescaler values, that means we choose prescaler of 8. So instead, we divide this now with 8. And get 2,500. So yun yung dapat value ng ating timer period. And then there's one additional cycle for rollover. So we just subtract this by 1. So that is for this part. So this one over here naman, timer is configured to have a prescaler of 64 and a period register of 127. If the input clock is 8 megahertz, what is the timer period? Assuming one additional cycle is used for the rollover. So relatively more straightforward. So ang period register natin is 127 plus one additional cycle for rollover, yung actual period ng ating timer. And then since we have a prescaler of 64, we multiply this by 64 to get the total number of cycles. And now we have the total number of cycles. So 128 times 64. Which is 8,192 cycles. So that is what is represented by our timer. And then we multiply this by, or divide actually, by 8 million cycles per second para makuha yung actual na time delay. So parang natatawag natin dimensional analysis. 6. So this is in milliseconds 1.02. And then dito naman sa baba, medyo same, but instead of 127, we have 312. So 312. So that gives us 20,000. And then 4 megahertz this time. Which gives us 5.008 milliseconds. So Yeah, let's just finish the attempt. Hopefully. Submit all and finish. And bam, 5 out of 5. Sana all. Yeah, so that is formative quiz number 1. So ito si, going back to our set of slides. So that was concerning timers. So next is ating interrupt latency or CPU percentage din. So yung ating interrupts, of course, we want them as short as possible. So when we evaluate our interrupts, we usually consider yung number of instructions na ginagamit sa ISR or number of clock cycles na kailangan sa ISR. And then you translate that to actual time or latency when we divide it by the clock cycle frequency. And then we can also, especially for interrupts that occur multiple times or regularly, we have what we call as ISR CPU percentage, which represents how much of the time ng ating CPU yung dinedevote natin uh, to to servicing interrupts. So if, for example, meron tayong analogy, yun nga, kuwari nag-aaral tayo and we have interrupts ng ating online shopping deliveries. So if our online shopping deliveries occur at a high rate, so kung madami kayong orders or mataas yung frequency, tumataas yung percentage ng time mo na i-devote mo sa pag-receive nito over doon sa ating pag-aaral. And for example, if matagal ka magbayad, daming instructions bago makapagbayad, dumadami rin yung time natin na devote for the interrupt instead of our main program. So let's just look at formative quiz B for this to have some examples. Continue last. Okay, so the first question is, consider a shadow register set that reduces the execution time by 2 ISRs and the execution time of 2 ISRs by the same amount, but can only be used on one of them. Using the SRS on which ISR will reduce the CPU percentage by the greatest amount. So, CPU percentage natin, looking back at our slides. So, I'm going to check. So, instructions times frequency ng ISR divided by the clock frequency. So, if more frequent yung ISR, yung CPU percentage niya will be higher. Pag less frequent, lower. Pag longer execution time. So, how do we actually answer this? So, for example, pag si IISR, binawasan natin, namumultiply pa siya by the frequency ng ISR. So, if mas mataas yung frequency ng ISR, mas malaki yung sinusubtract or mas lumalaki yung negative term dito sa ating numerator. So, we'd expect na siya yung mas mataas na reduction sa CPU overhead. So you can test this out by using some arbitrary numbers. I think dun sa mga examples na binigay ko on the weak materials, mayroong example dun na gagamit ng shadow register set. So pag ginamit natin siya sa longer or shorter execution time, since same amount lang yung nare-reduce natin, so yung overall effect niya should be relatively the same. And then, instruction frequency, parang sinabi, yung instruction frequency is related to the execution time. So if our answer is among these two, dapat answer din yung letter E. So that eliminates those three choices. So yung either more frequent or less frequent na ISR. Tapos pwede mo rin isipin, ano yung mas gusto mong pabilisin na ISR? Yung mas madalas mong gamitin or yung mas madalang mong gamitin? So of course, yung mas madalas gamitin, gusto mong bawasan yung execution time. Then, pwede mo isipin, gusto ko bang bawasan yung execution time ng mas mahaba or yung mas maikli? So, parang hindi masyado nagmamatter if mag-reduce ka lang by the same amount. So, most appropriate answer yung ating letter A. Okay, next question. Consider a timer interrupt that is configured to occur every 1 millisecond with an ISR that finishes after 124 instruction cycles. So, assume 3 megahertz na instruction frequency and yung ISR CPU percentage. So, siguro, write natin yung ating equation. ISR percentage is yung ISR instructions times yung frequency and yung clock frequency. FC. Oh, na. So, yung instruction cycles natin is 124. Ang frequency natin is occurs once every 1 millisecond. So, ang frequency ay 1 over 1 ms. Or, this is 1 kilohertz. And then, yung ating instruction frequency ay 3 megahertz. So, calculating, that is 124 times 1,000 over 3 million. So, ayan, answering percentage rounded off to 2 decimal places. So, what I get here is 0.04133 or 4.133%. So, ang lalagay natin dito is 4.13. So, for the next question, similar setup, except this time, ating interrupt ay configured to occur every 7 milliseconds. And we have 64 instruction cycles this time. 64, and we have 8 megahertz. So, 64, tapos 7 milliseconds times 8 megahertz. What you'll get here is 0.00114. So that is 0.11%. Okay. Then let's. So 2 interrupts have execution times of 3.2 and 2 microseconds, respectively. If both occur at the same rate, so 2 ISRs dapat actually instead of 2 interrupts. So what is the maximum frequency that they can occur to maintain a combined CPU average below 1%? So parang babalik rin lang natin yung equation natin kanina. So yung 1% should be, yan. Kailangan ng CPU percentage natin is below. So, ISR. So, execution times na yung binigay. So, gamitin natin, isulat lang natin yung other equation natin, just this one, sa kanan. So, basically, yung execution time ng ISR times yung frequency ng ISR is yung CPU percentage. So if we want our CPU percentage to be below 1%, so CPU below 1%, And we have yung execution times natin that occur at the same rate at 3.2 and 2. So ano yung FISR natin dito? So basically, isolate lang natin. FISR natin should be less than 0.01 times 5.2 times 10 to the negative 6. 3.5.2, which is di pala multiply. This is divide. So ulitin natin. So yung 1% divided by 5.2 microseconds. So that gives us 0.01 over 5.2, 6, which is 1923.077 hertz. So in kilohertz, that is 1.9. So similarly dito sa baba, we have and similarly dito sa baba, we have 1.7%. This time divided by 7.2 plus 9.6. Gives us 1011.9 hertz, which is 1.01 kilohertz. So yeah, let's just finish the attempt. Hopefully we got them correctly. And 5 out of 5. Galing talaga natin, guys. So, that will be yung ating mga calculations for week 12.